Welcome to the another session in Frontiers in CFD. CFD simulation of lithium-ion battery cooling using capric acid as a phase change material. Today's objective to generate 3D geometry of battery pack with PCM, to generate mesh on computational domain, apply the name selection, to define material model selection and run the iteration. Welcome you all. Today we will see the CFD simulation for thermal management of lithium ion battery. So this is the geometry which we are going to follow from one of the research paper. So let's start with the workbench. So the first phase will be preparation of geometry of lithium ion battery pack, and then subsequently we'll do the meshing, applying the boundary conditions, and accordingly we'll go ahead. So we'll be using 3C rates, that is 134 135.79 watt per meter cube, and we'll be using capric acid for the phase change material. So the capric acid properties are also been available with the paper, so we'll be using the same properties which are available, and accordingly we'll go ahead. So you can see here, so capric acid is available. With this configuration we'll try to prepare the geometry. So okay, so workbench window has opened. Now let's click on the geometry part, click on new design modular geometry. So first of all, set the units to millimeter. Click on any one of the plane so that XYZ will be visible to us. So go to create, take a primitive. So we need a box dimension, that is 92 here, 92 here, and 92 by 65. So X component I will take 92, Y component I will take 65, Z component I will take again 92. So instead of add material I will make it add to frozen. Let's make it generate. So you can see here the box has been generated. Now I need to prepare sketch for the cells here. So on ZX plane I will create the sketch. So draw a circle here. Dimensions of the circle, diameter will be equal to 18. Distance from one end to this I will say here. So this is 9 plus 4, I will take it 13. Similarly from this point to here I will take it 13. So this is the first which has been prepared. Now accordingly we need to prepare the similar second also. So first of all, drawing any line here. Okay, so the dimensions for this will be 9 plus 9, that is 18, plus 4, that is equal to 22. So we need to draw one more circle at that particular distance. Okay, so first of all let's complete the lines. One more line here, that will be 22. Then one more line usually corresponds to 22. Now draw one more line which is from here. Dimensions will be 22. Again the same dimensions will be equal to 22. So we have to carefully select all the points to avoid the errors in the later stages. Okay, so this is done. Now go to the modify, click on copy, select this, select set paste handle here, here, and here. So the first phase has been done. Now one more time select this, this, click on copy, click it here, So you can see now all cells are being generated. Now simply go to the extrude, select on sketch. Instead of add material, now I will do slice material, make it 65. Just have a visualization of this and let's make it generate. So you can see now the geometry has been generated as per what it is specified in the paper. So 92 by 65, so they are done. So we have not considered here casing, but the casing can also be added to the cells. Okay, so let's see which is the fluid zone. So this is your, sorry, this is your PCM zone. So I will just define it here, PCM. Rest of them will be your cells. So this will be solid again, keeping, I will form new part for this. So we'll denote this as your cells. So one by one I will change name for all others inside. For this again we'll take it cell. Here also let's make it cell. Here we'll put it cell. Then here as well we'll put it cell. Here also we'll put it cell. So all the names you have to do as a cell. So once all the name has been done, you can proceed. Okay, so one of them is PCM, second one is your cells. So all the name definition has been done. Now it's time to proceed for the next step. So let's click on save button. So give the name to the file. I will put 16 cells with PCM. Here also I will give the name 16 cells with PCM. So once the file is saved, you can access the file later on also. So that is the advantage when you save the file. So just click on edit. So we'll see one more time the paper. So they have used various mesh numbers. So we'll select any one of them from the one which is suitable to us, considering the uh, limitations of nodes and element and computational capabilities. So accordingly we'll select this. Okay, so if you find such thing, close the window and open the mesh again. So go back to the workbench window one more time, just click on edit. So you can see now it is visible. Make it fit to window and accordingly. So first of all I will just generate the default mesh in order to understand how many number of nodes and elements are been there. So it shows around 47,251. So what are the end limit which we are observing from the paper is around 4,89,251. So we'll try to go which is near to that value. So let's put the element size 0.005. Let's generate the mesh. Okay, so no change at 0.005. So let's make it 0.0025 and see what changes occurs. So slightly the things have changed. I will make it 0.001. So it is 79,000 as of now. Generate mesh. Now this will be further modified. Okay, you can see now this is becomes 11,43,020. So this becomes slightly on the finer side. You can actually go away uh, with this particular limit as well. So let's make it 0.0015 and just check it what happens. So this will be in between the previous one and this one. So here you will see 3,59,100. So I'll just put it, let us say, in between value. So more the number of nodes and element, more accurate will be the result. So we may try for this is 6,79,728. So this is quite higher than that. I will just try to prefer it 0.001 and will make click on generate. So I will keep the same value, which is around 10 lakh, and will proceed for the next part. Okay, so this is 11,43,020, that is the nodes, 10,56,792, that is the elements. Okay, so now this is what I have finalized. So I just go with the geometry, say I hide all other bodies. I will select all the cells, walls right now. I'm selecting all cell walls here. So I just define this as cell boundary. I define this as a cell boundary here, and this is your PCM. I will just this will be as it is. I'm not going to change anything. There is no inlet and outlet, so there is nothing to specify other boundary conditions. So just click on update. So once you click on update, just click on close meshing part. As I said, you can make it further fine as well. So we'll just go with the same nodes and element which have been available. Now just click on edit. So the setup window will open. Click on double precision. I will just put it to 18. So make it start. Now it's the step towards the setup part, where we need to define the models. We need to define the geometries. We need to define the materials as well. We need to define the cell zone conditions also. So that is one process which we have to follow in the next step. Okay, so just click it here, select transient. I put it gravity, say minus 9.81. Go to the models, energy equation, I will turn it on, make it okay. Then viscous, I will select K epsilon, enhance wall treatment, thermal effect, curvature correction, make it okay. Then I will select solidification melting, turn it on, make it okay. Then go to the materials. So we'll put the properties as per what it is available from the table. So nothing is mentioned regarding to the solid and liquid. So capric acid 878 as your density. So I just put it here, capric acid. So we need to define both solid and liquid. So I'll just put it capric acid liquid now. Put the value of density 878. Specific heat 2250. Thermal conductivity 0.153. Then viscosity is not mentioned here, so we'll put the value 152,700. Pure solvent melting heat. Then solidus temperature and liquidus temperature. So 302.15 and 305.15. We'll just check out viscosity for capric acid. So this is at 50 degrees Celsius, it is showing 0.0043. This is at 70 degrees Celsius. So let's make it change grade. So this becomes your capric acid. So first of all, we'll specify lithium battery. So lithium battery here. So just go to the table one more time and see the properties of lithium battery. Okay, so you know specific heat, density 2782. This is 2782. Then specific heat 1087. 1087. Thermal conductivity I will take it radial thermal conductivity 1.2743. Just make it change grade. Okay, one more thing we have to add, that is your solid. Let's put aluminum here. Make change grade. So I will here put capric acid solid. Here I will put capric acid solid. So again we need to go for the properties. I think as per the table there is only one values are given, so we'll use the same. $878. It is your density. Specific heat 2250. Thermal conductivity I will put it again 1.73 as it is. Let's make it okay and click on close. So material selection has been done. Go to the cell zone condition, observe it by zone types. So this will be your solid here. So capric cells are the solid material. So we have to define the material of the cells. So select lithium battery, select source term, go to edit, select the number of energy sources. I put it this value. Now again you have to go back and see the heat generation per unit volume for 1C, 2C, 3C and other values. So this was available at the start. So 134, 135.79, 134, 135.79. Just see one more time. Make it OK. Click on apply. Click on close. Just go to the PCM fluid material. By default it will be the capric acid liquid. Then go to the boundary conditions. You will see now cell boundary contact region. Just check here the material. The material should be the lithium ion battery. So yeah, this is there. So just you have to check it. So here wall cell, lithium battery, wall PCM. I need to change this material now, because by default it will show you lithium battery. I will capric acid solid. So make it apply and then close. Okay, so if some convective heat transfer coefficient has to be applied, it can be applied on the cell boundaries and so on. So here nothing is specified, so we'll go accordingly. So go to the report definition. Okay, first of all, what I will do, I will go to the initialization and then we'll come back to report definition. So first of all, click on initialize. Once it is initialized, you will see calculation activities option. Just click on 20. Here, go to the solution animation. Now this is a very important task. So I will just select first temperature. I will select total temperature and I will select only cell boundary contact regions only. So that will show me cell temperature only. Okay, so this is cell boundary contact region. I will select wall cell. So make it float. Click on apply. Then close. So this is your contour 1. You will see the cells will be visible. Close this, select contour 1 and define this as cell temperature animation. Make it OK. Go to one more time here, new object, contours. Now I will select solidification melting. OK. Now select the PCM. Wall PCM is there. Now you have to do this carefully now. So just for understanding, first of all, click on display. So you will see it looks like a hollow part. So now I will just go on to select one by one the regions. So we'll make it slightly on this side. Click on save display. You will see now this has getting filled. So one by one just check this portion is getting filled here. So here the third one. You can see now things has okay. So this is next, see one by one how the changes are taking place. So just see how many are left now. Okay, one is left. Okay, now this you can see it is completely filled. So click on save display, click on close, select contour 2. I will say liquid fraction now. Okay, so select on liquid fraction, make it okay. So just you have to remember this. One more thing, I will see contours. Now here I will select temperature. I will select the total temperature and select all. So make it float, make it apply, then close, click on save display, close, click contour 3. So I will select now total temperature system animation. So these are the three things we are defined. Now accordingly I will go to the report definition and will define the things. Surface report. So here I will select temperature first. Cell boundary contact regions I will select only in order to know the cell temperatures. So select all here, print to console. So define here cell temperature. So also create output parameter and we'll select the wall cell and let's make it okay. Next, surface report, area weighted average. Here I will select temperature. I will select total temperature, print to console. Here I will put total temperature system report definition. So let's make it okay. Third, I will select surface report, area weighted average. Now here I will use solidification melting, liquid fraction. Now where the liquid fraction is available, wall PCM and your contact regions, which we have selected during the animation. Why we have done that earlier? Because we are understood where are the zones. Now this geometry is simple, that's why it becomes easy. But if the geometry has multiple things, so in that becomes very difficult, and that's why it is always important to see where the object lies, and then accordingly we have to proceed. So here I will put liquid fraction report definition and let's make it okay. Once this is done, you just go to the run calculation and select the number of time steps. Let us say initially I will put it to 10 and let's have the initial run for this particular case. So we need to run it further for a long time in order to ensure that the solidification melting occurs. Till the time you don't see the solidification melting, you have to keep on running the simulation. So based upon the heat generation per unit volume, we have started this particular simulation. So after the first 20 iterations, you, you will be able to see all the graphs which are been generated, whatever report definition we have set, as well as whatever the animation we have set. So all this will be visible once the first 20 iterations are been completed. So you can see 1 2 3 4 5 6 now. So once this all 20 are completed, you will see the window will show the various cases which we are defined, like cell temperature, then total temperature of system, liquid fraction. Then in solution animation we again set the same thing, total temperature of system, cell temperature of the system, and then the liquid fraction. Okay, now you can see first 20 iterations are completed. Now you one by one you will see the temperature rise, as well as you will see the cell temperature as well. Okay, so what we can visualize over here. So let's take, this is the contours of total temperature of the system, sorry, cell. This is the liquid fraction which is showing 0 right now because the melting hasn't occurred. Then this represents the total temperature of system including cells and your PCM. So this represents the liquid fraction which is 0 as of now because the melting hasn't started. Then this will represent the total temperature of system, temperature is rising. This will represent the cell temperature. So again you can see the temperature rising. So here we have to wait for some time till the melting occurs, and accordingly we can visualize the liquid fraction as well. So 300.13, this is the temperature which is the maximum temperature which we can see right now. So liquid fraction as of now it is not there, but as soon as the melting occur, you will see the liquid fraction also visible here. So this is again the curve. So we have to wait and for the iterations to complete, for this temperature to reach to whatever the solidification and melting temperature we are specified, and accordingly we have to proceed for the simulation. So we'll put it some to a higher value. Just now we have put it around just only 10 seconds. So we'll put it 100 or something, and accordingly we'll be able to visualize the change in temperatures, and as well as we'll be able to visualize whatever the liquid fraction which has been present. So the first 10 iterations have been completed. You can see the variations as well in terms of the total temperature of system which has been available. So let's click on come OK, and then go to the workbench window. Just click on save button. Once it is saved, we will run it for further 100 iterations. So I just put it 90 now. Okay, so we'll wait for some time, and then accordingly we will visualize what happens at the end of 100 seconds. So the first 100 time steps are completed. You can see calculation complete message option appears. So this represents the cell temperature. This represents the liquid fraction. You can see now a liquid fraction is visible. Earlier it was showing 0, 0. So you can see the total temperature system. Again, the liquid fraction curve goes up, as you can see here. Earlier it was showing as a flat curve. And then this is your total temperature of system. This represents the cell temperature. Okay, so let's click on save button. Then we have to run it further. So we'll run it further for 100, and accordingly we will visualize the things. So the liquid fraction is right now 0.01 right now. So this may rise to some higher value. So we'll just carefully look at how things will change after 200 time steps. Now the 200 time steps are completed. You can see the calculation complete of message. See the total temperature of the system. This represents the contours of liquid fraction. 0.39 it is showing. Then this represents the total temperature of system, liquid fraction. Again the curve, total temperature of system, and this is your cell temperature. So we'll save the work and we'll run it further for another 100 time steps. So we are near to 300 time steps. So 6 time steps are remaining for 300. You can see the curve, that is cell temperature likely to getting flat. This is the total temperature of system. So liquid fraction, you can see gradually it is rising. Then this is total temperature of system. Liquid fraction reaches to around 0.65 as of now, and this is again the total temperature system. So in this way we have proceeded for the simulation. So once the calculation is complete, we will run it again for further iterations. Run the simulation for around 530 seconds. You can see now contours of total temperature system, contours of liquid fraction, contours of total temperature. Then this is this is the contours of cell temperature. This is the total cell temperature curve, total temperature system curve, and you will see the liquid fraction. So liquid fraction is gradually becoming flat. So this is up to the iteration which we have performed for around 530 seconds. So let's click on save button and run the calculation again. Now 600 seconds are completed. You can see the contours of total temperature for cell. Here you will see the contours of liquid fraction. Next, contours of total temperature of system. Here you will see the cell temperature curve. Then you will see the total temperature curve, and you will see a liquid fraction curve, which is slightly become flat. So this is your scale residual. So we have run it around 600 seconds. So we'll save the work. Let's run the animation. Go to the playback. You will see 1 to 600 seconds. So you are observing a video file here, cell temperature animation. So you can just click on play button and you can visualize how the cell temperature varies. So this is one way by which we can visualize the simulation. So if I go with the liquid fraction here, now this is 0 point. So this is the replay speed I am having. If I just click on this, you can see this is 4, 5, 6, 7, which is changing. So I will select a different interval. So I will select the higher speed. Now we'll see how things goes. So carefully observe in this particular region. So total 40 seconds right now. So we don't observe any liquid fraction as of now for first 60 seconds. Okay, so you can see here slightly the liquid fraction is getting visible for around 60 to 70 seconds. So this represents the increase in the liquid fraction. Earlier it was a PCM solid. Now it is the PCM is melting. So you can see the change in the frames. So gradually this will increase as continuously the heat is being generated by the cell. So the PCM, which was initially in solid state, now it will melt, and you can see the liquid fraction increasing, that is 0.23 and so at the top scale. At the bottom scale you are observing 0, 0. So this will continue till 400 seconds. Sorry, 600 seconds. Now we will see how the total temperature of system varies with respect to time. So I just click on display. Now you can see the variation as you can visualize over here. So they are clearly visible how the temperature changes have been taking place. Earlier we have run it for 1 as an increment. Now I have run it for 10 as an increment so that we can visualize it in more better way. So this run is done for 600 seconds. So you will get the results for 600 seconds. As we have observed, the liquid fraction curve become flat after some 600 seconds. So we'll stop our iterations at 600 seconds. Six hundreds are completed. Now we will see the cell temperature. So again, let's click on play. Let's start with the cell temperature. You may observe some variations in terms of temperature. So one more time, liquid fraction. So after 70-80 we have seen some variations in terms of liquid fraction which is present. So that same we are able to visualize it here. We have taken 10 increment as an interval so that it will be quite better to visualize rather than the single one, as it takes time. The video represents the simulation of contours of total temperature of cell with respect to flow time. So you can visualize how the cell temperature varies with respect to time. So total it is done for 600 seconds. This represents the liquid fraction up to 600 seconds. And lastly, it represents the total temperature of system. Again done for 600 seconds. The graph represents liquid fraction with respect to time. We have completed 600 seconds. For the 600 seconds, you can see initially the curve was flat, then liquid fraction increases, and again the curve becomes again flat. So this represents the cell temperature with respect to time. So total around 600 seconds are completed.